Yes, you can start.
So, hi everyone. I'd like to welcome each one of you to the Param-Intelligence seminar series, which is particularly dedicated to advancements in scientific machine learning. Today we have with us, and we are pleased to have Dr. Ján Drgoňa. And Dr. Ján Drgoňa is an incoming associate professor in the Department of Civil and Systems Engineering and Ralph S. O'Connor Sustainable Energy Institute at Johns Hopkins University, and currently works as a senior data scientist in the Physics and Computational Sciences Division at Pacific Northwest National Labs. Dr. Ján has a PhD in controls engineering from Slovak University of Technology in Slovakia. And before joining PNNL, he was a postdoc in the mechanical engineering department at KU Leuven in Belgium. His current research is focused on physics-informed machine learning for dynamical systems, constraint optimization, and model-based optimal control with applications in the energy sector. So today, Dr. Ján is joining us to give a talk on the title, which is closely related to his work and his research, which is differentiable programming for data-driven modeling, optimization, and control. So, and I'm particularly looking forward to learning a lot of this during this talk. So over to you, Dr. Ján.
Thank you very much, Sindar, for the introductions, and thank you very much for having me again. I want to focus not only on theory today, but mostly on software implementation of these new machine learning methods for data-driven modeling, optimization, and control. And specifically, I will be talking about the Neuromancer library that we develop at PNL with my wonderful colleagues, Aaron Tour, Madeline Shapiro, Rahul Birmivar, James Cook, Bruno Jacob, and Draguna Vrabje, who contributed to the library over the last 4 years. And the motivation started from the application areas that we are dealing with at PNNL. And it's broadly Department of Energy portfolio, whether it is building energy systems, power systems, floating offshore wind turbines, or optimizing traffic flows in cities, or some submersible underwater vehicles. These are all physical systems that can be represented as a complex systems for which we very often have some high fidelity simulation models, but they are not suitable for closed loop decision making and control. We can do forward simulation, but it's very, very hard to do any optimal design, any optimal control because they are so computationally expensive and they are not suitable for gradient-based optimization with our existing tools for optimal control. So what is promising in the future is to come up with some reducer models, some maybe machine learning based models that will allow us to do optimal control and decision making. But the challenge here is that there are heterogeneous modeling methods when it comes to modeling these complex systems. When we have the high fidelity emulators, most often they are component based emulators implemented in MATLAB Simulink or Modelica language or some domain-specific language like Energy Plus, which are purely engineering-based, manually designed models that can take months to develop. On the other hand, when you look at what is called world models these days in machine learning, you have mostly black box architectures, like purely black box multi-layer perceptrons or some transformer architectures, or recently rediscovered state space models are being used to model these dynamical systems. And in between, there is wide area of gray box modeling that is emerging as promising research area. So, but still, there is no unification of machine learning and these component-based, physics-based models in a coherent framework that we could use in optimal control. Challenge number two is that we have also heterogeneous solution methods. When we are talking about domain-based methods in our engineering, we typically solve optimal control problems with constraint optimization. So for people who are familiar with model priority control, we formulate our objectives, our constraints, and we transform this optimal control problem into constraint optimization problem and solve this with appropriate solver, whether you're using quadratic optimization solvers or nonlinear interior point solvers. That's how we solve optimal control these days in real time. And similarly, in differential equations, you need to have the right-hand side of your ODE or PDE, and then use appropriate solver to basically obtain the solution forward in time. And these are all physics-based. And how machine learning community solves these problems, you either have supervised learning approach, where you have large labeled data set of your dependent and independent variables, and then you choose appropriate architecture to fit this function. Or you have some digital twin or emulator or environment that you can sample and receive scalar valued reward signal. So you can learn control policy with this actor critic reinforcement learning approach. So these two communities have been separated in their theories and the way how they approach problems for, I would say, many decades. But now what we see is more like convergence. More machine learning is being used to accelerate constraint optimization and approximate unknown terms in differential equations, and more procedural models are being used as layers, as structured priors in either supervised learning or reinforcement learning paradigms. But this division also has historically separated the tools that we are using. So in constraint optimization, we are using these algebraic modeling languages like PyM or JAMP or Gecko and Casadi for dynamic optimization that allow you to formulate your optimization or optimal control problem in higher level abstractions and then translate these higher level abstractions into solver specific formulations. So you can use state-of-the-art solvers like Gurobi or Cplex. In differential equations, very similar story. There are a lot of libraries that are generic or domain specific for specific type of systems like power systems or molecular dynamics that allow you to solve large scale differential equations. But really the revolution in terms of the tools came like a decade ago with introduction of machine learning libraries like PyTorch, TensorFlow that made it so easy to use deep learning that now you see it everywhere. So the user friendliness is really a great feature of those libraries that allow the widespread success of deep learning architectures. And what we see there is emergence of new libraries and new languages that allow automatic differentiation, which is the workhorse of deep learning, not only for black box models, but now basically merging our component-based or equation-based modeling from engineering into these machine learning flat frameworks like Julia, PIML, ecosystem, or JAX. And this direction is often called scientific machine learning or physics informed machine learning or differentiable programming that allows that. So the systematic combination of our mathematical models and algorithms that we developed in various engineering domains with deep learning architectures. So why would you like to do that? Well, we know these physical principles and constraints, and we want to satisfy them. So we don't want to throw them away and learn them, rediscover them from data if you already know them. And we want to have some performance or safety guarantees in many application areas, especially in control. So these scientific machine learning methods bring promise of that. And how we train them is the same way how we train deep neural networks. We use automatic differentiation, which has been here for many decades also from engineering. But what is different now is the ease of use, that these new libraries really allow a differentiation of complex computational graphs, which is another word for these neural architectures, that can be served multiple application areas without too much of the computational overhead or too much of the coding required from the user. So when we are talking about scientific machine learning methods, so what do they represent? High level picture here. We can roughly separate them into four main components. So you need to have some data because these are all data-driven methods. And you either obtain them with some active sampling or collocation pair point methods in partial differential equations or measurements when you want to deal with system identification. Then you have some machine learning surrogate model that can be the deep neural network in various architectures. And you have domain prior, which represents either your differential equation that you know beforehand, or some constraints you want to satisfy, or some transformation that will give you invariance to some measure. And the last component is the domain ever loss function. That's basically penalty method or augmented Lagrangian method, which we know from optimization. But now you are basically computing the expectations of these Lagrangian loss functions to obtain scalar valued loss that you can backpropagate in the reverse mode automatic differentiation through this computational graph to domain priors to obtain the trainable parameters of these AI or machine learning surrogates. So there has been a lot of recent research in this area. Only few review papers I'm providing over here. You can find way more in the Google Scholar or on arXiv that basically define what does it mean SciML and physical information learning, which become quite overloaded terms already. So when we started doing this research in 4 or 5 years ago, there was no open source software tools, and every paper came with its own implementation. It was very hard for us to integrate it in a deliverable for Department of Energy that would use, let's say, neural ordinary differential equations and then differentiable optimization layers in one package. So we started to develop our own library because of that. And we have been thinking, how do we make it very user-friendly and flexible at the same time? So we borrowed the API from operational research and control theory tools like CVXPy or PyOmo, where we formulate our constraint optimization problems with symbolic abstractions, which are these variable classes. So here I have simple optimization problem with nonlinear objective and some nonlinear constraints, where I have some decision variables and parameters that shape the objective function and constraints. So for those, I will be instantiating them as variables, and we allow these inline expressions to be instantiating our objectives and constraint terms. So this is very similar approach like you would have in CVXPy or PyOmo. You write your objectives and constraints in a list of objectives and constraints, then you aggregate them in some optimization problem. And here what we provide is that you can aggregate them with some machine learning components. Here I have multi-layer perceptron that I've wrapped in our node class that represents the symbolic wrapper that basically allows it to be linked to these symbolic variables. And I will explain in detail how we do that in the coding examples. But that's the general idea, to write this high-level abstract problem in symbolic form on the top of PyTorch, and behind the scenes in the backend, our library will generate computational graphs that represent these custom neural architectures for the scientific machine learning models that you can train with standard stochastic gradient descent, what is already in the PyTorch library. Good. So the next step, I want to go through our GitHub page. So if you want to go with me, you can either type this github.com/PNL/Neuromancer or scan this QR code to get to the GitHub page, and we will go through 4 examples together. Learning to optimize, learning to control, nonlinear system identification, and physics-informed neural network. And I will try to make the point, although these are different methods that have been developed by different communities, the underlying principles in abstract space are very similar, which allows us to design unified API for all of these. So there will be only a handful of abstractions that will allow us to implement all of these 4 categories. So I will land at this GitHub page. And the first point of contact is our README. So we have short paragraph about what Neuromancer is. It's a differential programming library for scientific machine learning methods. Is written on top of PyTorch. The PyTorch was a conscious choice because it's the most popular deep learning library. It's very flexible in terms of modeling your problems, very easy to use, modular, and has great support from the community and on the CPU CUDA compilers, so you can scale these problems easily on GPUs. The next part is our release notes, what is new in each version. And then we have examples, right, where probably everyone should start to get like the first.
Jan, just one comment. We cannot
Yes.
see your, we are just seeing your slides. We cannot see the web page.
Okay, let me share again.
Thanks.
Thank you. How about this?
Yeah, that's perfect.
Yes. Good. I think I was sharing only one screen, one window. Good. So I'm at this GitHub webpage, and I was just going through the README, through the release notes, and I'm here now at the features and examples. Where are we going to start the tutorial? And here are really like the introduction on the syntax of the classes that we are using to construct these scientific machine learning models. I'm going to jump right into one of the examples, which will be these physics-informed neural networks, because they are probably the most well-known scientific machine learning method out there. And here is a simple diagram of the whole method, where you have a neural network that maps the problem parameters of the PDE, which are spatial and temporal coordinates, into the solution of the PDE. But instead of training this in supervision, in imitation, where you would have pre-computed solutions of the PD and try to minimize the residuals of this neural network from those pre-computed solutions, here we don't have those pre-computed solutions. Instead, we have our PD equations, which we want to satisfy as a constraint in this learning problem. So how do we do that? Well, all the technical details can be found in the original papers. We do that by taking this PD equation as a layer in deep neural network. So this is the diffusion equation that we know, and we know some initial and boundary conditions. And we want to solve this with neural network using collocation-based approach. So first, this is how the diffusion equation looks. It's a textbook example. So first, I'm going to sample the collocation points, initial conditions, and boundary conditions. So I'm going to skip the code details, but here is how it will look. This is simple 2D PDE, where I have one spatial and one temporal coordinate. And here the blue dots represents the collocation points. So for each point in space and time, I will be evaluating this neural network forward in time, obtain the solution or the candidate solution that neural network will propose, and evaluate the PD constraint. And the residual of the PD constraint will serve as a loss signal for computing the gradient backward in time through the computational graph. The red dots here represent initial and boundary conditions that are supervisory signals, because here we assume we know the solution. So the blue dots are unsupervised or self-supervised data points, and the red ones are supervised. So the next step is the neural architecture, which can be really anything. In this case, I have very simple multi-layer perceptron with only 2 layers, 32 neurons each, with tanh activation function, which will map my spatial and temporal coordinates into the PD solution. So in PyTorch, for those of you who are using PyTorch, you know, like these architectures are NN modules. That's the base class in PyTorch for implementing any neural network, what we provide is this wrapper, that is the node class, that takes any NN module, or in general, any callable in PyTorch, and wraps it as a symbolic layer, where based on the positional arguments of this callable, we will label those positional arguments with these strings, which represent variable names. So there will be spatial and temporal coordinates mapped to the y hat, which will be the solution to PDE. And PyTorch is basically tensor to tensor mapping. Right? That's any neural network architecture. Here, this will be dictionary to dictionary, where the keys will represent the variable names and the values will represent the tensors, the numerical values associated with these variable names. So that's the only difference in our library compared to PyTorch. But now I have this data set of sampled collocation points. I have machine learning architecture. The next is to provide that domain or structural prior, which will be this PDE equation. So this pin layer is a mapping of spatial temporal coordinates into this expression that requires partial derivatives of my neural network with respect to temporal and spatial coordinates. So how do you obtain this? Well, we can use automatic differentiation again to obtain these gradients and implement this expression as a layer in the computation graph. So how do we do that in our library? It's very straightforward. We just instantiate these variables. The y hat, that is the output of the neural network, that's the PDE solution, and spatial temporal coordinates t and x. Then we can use this grad method, which under the hood calls PyTorch autograd, to basically instantiate that forward pass that implements the automatic differentiation. But here is just one line of code. That's a symbolic gradient variable that allows us to instantiate them and use them in another expression that represents the pin layer. And you see that it can handle arbitrary PyTorch expressions. So it's exponential here, it's some trigonometric functions, some constants that are still represent differential layer. Yeah, because when we instantiate these variables, there are still NN modules in PyTorch. That means that they have forward pass and they are differentiable in backward pass. And you can also do this dot show method that visualize this computation graph of this pin layer. It's a mess because there are many terms, but it gives you an idea of what are you differentiating through. So next, the final step is you need to have the loss function. And the pins are sampled over collocation points. And I have this NF number of collocation points. And we want to satisfy the PDE constraint over those collocation points. So basically, I'm penalizing the residual of this pin layer. Because if it converges to 0, it means that PDE is satisfied. So that's my first and most important objective term in pins. Then I have initial and boundary conditions that are supervisory signals, where the neural network will match some signal that we already know on those initial and boundary conditions. And I can add arbitrary number of additional constraints. So here is example of adding the domain constraint on the neural network, because I know the PDE needs to be bounded between -1 and 1. So I just do that with these ReLU expressions, which are clamping the values that are above or below and penalizing them. And then I add all of these terms in single loss function that will be my trainable loss function for obtaining the scalar valued signal that I can differentiate backward in time. So how I'm implementing them is very simple. It's a few lines of code again, because I have this pin layer. That's the collocation point. So I want to basically be equal to 0 over all tensor values. Then I'm picking the initial and boundary condition supervisory signals over here, and I'm making it equal to my solutions at those points. And I'm incorporating these inequality constraints to clamp the boundary of the PDE solution generated by neural network. So I have four terms here that I list as list of objectives and constraints and construct a differentiable loss function. There are different methods how to do that. The most simple one is the penalty method, just to penalize the violations of those expressions in like the weighted term, and then compute the expectations of them by sampling them over the samples of the collocation points. More advanced approaches could be using augmented Lagrangian, where you also have some information about dual variables, or using barrier functions or penalty barrier functions instead of just penalties to also give you the gradient in the interior of the feasible region. There are a lot of variations how to do that. Or also instead of this fixed scaling factor, which becomes quite important in larger scale problems or multi physics problems. These can be also designed in algorithmic way. They are like adaptive weighting terms in pins. There's a lot of research on how do we actually make them well posed numerically. The convergence can be an issue for complex systems here with this naive approach. So that's what is basically in this aggregate loss function that brings together all the objectives and constraints and formulates them as a single loss function. Then we construct this optimization problem that has list of nodes that are either neural network architectures or any callables that are differentiable. This aggregate loss function, and it still represents your custom neural network architecture, if you will. It's still an module in PyTorch. So this problem will be trained by standard stochastic gradient descent. So in this case, it's ADAM optimizer from PyTorch. We have provided the trainer that takes this problem, the dataset and the optimizer, and specifies number of epochs to train the model. And after convergence, you should see the solution of the pin in this case, in this example. And then you can compare it with the ground truth solution and evaluate the residuals between, so what are the errors. So that's basically pin in a nutshell, how people solve this. There is a lot of research in what neural architectures you should use, what loss functions you should use, how should you scale these weighting factors, and yeah, how should you train it in terms of like what optimizer and what heuristics in optimizing stochastic gradient descent you should use. So it's basically becoming a research field on itself. Are there any questions on pins or this particular example? So if not, I'm going to move to another example that is called learning to optimize. And this is operational research community that is developing these methods that are aiming to solve constraint optimization problems that emerge in transportation, in logistics, in power systems. In general, you can formulate them in this form. You have some objective function that you want to minimize. You have some primal decision variables, x, and some parameters theta that can change objective functions or constraints. So this is general nonlinear parametric programming problem. There are no analytical tools that allow you to solve this parametrically. So how they are being solved is through real-time optimization. So for one specific instance of the parameters theta, we are solving this problem iteratively using interior point or other solvers. So here the idea is to replace the interior point with neural network. And instead of per instance basis, let's solve this as a machine learning model. Over the distribution of the problem parameters, let's give me the distribution of my primal solutions. So conceptually, this is very similar to physics-informed neural networks, if you see that, because this is your neural or like machine learning component. This would be your domain prior, and the data set will be sampled collocation points in this parametric space theta. And again, there are a lot of publications, a lot of active research in this area. Also different terminology. People call it declarative networks or end-to-end constraint optimization or differentiable optimization. There are different terminologies for that because it's a very new area, and there are contributions from different communities. So I want to make it a little bit more tangible with one specific concrete example. So I have this Rosenbrock nonlinear objective function where you have primal decision variables x and y, and you have problem parameter a. And then there is this nonlinear constraints where they are parameterized by p. So I have two decision variables and two parameters. And I'm going to sample the parameters again as a collocation points. And the blue ones represent this training data that I will be using in this self-supervised learning approach. So A and P, one parameterizing the loss function, one parameterizing the constraint. So here I'm obtaining the neural network instantiation, and maybe I can run this so I can play with it while I'm talking. So this neural network will be mapping these problem parameters A and P into the primal decision variable. So I'm using multilayer perceptron again, and I'm using the same node class to wrap this multilayer perceptron in this symbolic expression that will be mapping variables A and P into decision variables. All right, so this is standard neural network approach. Then I'm instantiating the variables that represent my primal decisions and parameters. And we allow very like expressive framework that you can have these inline expressions, you can have slicing of these variables to define your objective functions or constraints. So this is implementation of this particular problem that I have written over here. In few lines of code, you define your objectives, terms, and constraints the same way like you would do in CVXPy, let's say. And then I define the list of objectives, and I define the list of constraints and instantiate this neural network node that will be representing the parametric solution of the problem. Yes, and then I have this penalty loss function and the problem that will represent this constraint optimization. Okay, let me run this again from here. So what I just did, I was just installing all the dependencies in this first cell. So you don't need to install anything. You can run all of these notebooks yourself in Google Colab in your web browser. So now after installing the dependencies, I'm importing what I need for this example, which will be just pure PyTorch, our Neuromancer, and some matplotlib for plotting, and Kasadi is the nonlinear optimization optimal control framework that I will be using for benchmark solution for interior point. So here I'm just importing all the classes that I'm needing for this example. So I'm skipping the data generation and the architecture instantiation and constraints because we went through that already. I am here now into this problem that I'm going to train. And I'm going to train this again with this stochastic gradient descent, this A.W, and I'm going to train this problem parameters. So you see like in PyTorch, when you're implementing things, you would have your model parameters. Like here, this problem is still scientific machine learning model. There are trainable parameters to optimize, and I'm using this trainer like before. All the syntax is the same. I'm using the same abstractions to define physics-informed neural networks as I'm using it for learning to optimize for constraint optimization. And then I'm calling this trainer.train. That basically allows me to train this architecture now in a stochastic gradient way. It should be converging somewhere. I'm going to stop it and see how it worked after a couple of epochs. Here I'm getting one instance for one specific value of parameters and for the optimization problem, getting the benchmark solution with the Casadi, with interior point, and I'm comparing this visually with this Neuromancer approach using stochastic gradient descent. So because I didn't train it for long, if I would let it run longer, these two would be closer, but the green one essentially is the interior point solution, and this red one is the solution with stochastic gradient descent. So it's always an approximation, but what is advantageous here is every time we change parameter, which means like you shift the constraints or you change the shape of the loss function, you need to recompute the optimization problem again with the interior point, which is quite expensive. While in this scientific machine learning approach, learning to optimize, you have neural network that basically memorized the solution over distribution of parameters. And the inference time is orders of magnitude faster. And you may ask how much faster. So yeah, here I have evaluated 1,000 problems using interior point and 1,000 problems using this learning to optimize method. And the speed up is 3 orders of magnitude. Yeah, so it's 2,300 times faster to use this trained neural network to obtain the solution in real time for changing parameters. So you can see this can be very useful for any real-time optimization that has limited compute bandwidth, that you need to compute solutions in milliseconds, or you are having autonomous vehicle that has limited energy resources to make decisions in real time. So these are the compelling factors, really the acceleration of the solution, why people are making research in this. And also, like maybe let me visualize some other parameter. Going to for both. So I'm going to evaluate all of these cells, which will give me the benchmark solution with interior point solver. And I'm going to compare, and you should see, yeah, the feasible region expanded. Yeah. And again, I didn't train it for long enough, but if I train it for longer, the red solution is basically chasing the green solution. And this is the parametric solution of the nonlinear optimization problem. Are there any questions here?
I have one question. So,
Yes.
sorry, I have a noise in back.
Mm-hmm.
Just one request to all participants. Can you please introduce yourself briefly before asking any questions?
Yeah. So, can you see me?
Yes.
Okay. So, I'm a master student. I'm working on guidance, navigation, and controls. So, I have this question about you have changed the parameters here, right? So, let's suppose if you have to add some other constraints. If we're talking about path planning, optimal path planning, if you have some newer constraint, let's suppose to avoid some certain obstacle, would this be able to do that?
Depends how you formulate it. In principle, yes. Every time you formulate this problem, the constraints would already have to be there, but you can have a parameter that activates it or deactivates it. So in that formulation, yes, you can handle obstacle avoidance problems without problems. We already have done that for some obstacle avoidance problems, even with parametric, like moving obstacles.
Okay, right. So are there any examples available here or any papers for that?
Yes.
Moving.
So here I'm showing this parametric programming example. So maybe I can go, okay, this is our library. The first line of contact is all of these examples. So learning to optimize, I was just showing the simplest one, but we have way more over here. This is nonlinear system ID, which I will go through. These are the pins. This is learning to control, which is the closest to the topic you are asking. And some domain examples in energy systems. And these are scalability examples by integrating with PyTorch Lightning. When you want to like have GPU support or like hyperparameter tuning, this will help you a lot for dealing with larger systems. So also when you go to the example folder over here, we have a bunch of folders over here, but let's say in parametric programming, there are all the Jupyter notebooks and some write-up on the method and explanation of the method in more detail and code examples. So yeah, we try to like be quite comprehensive in the readmes and in also markup in our examples and providing all the references to the papers that we are implementing.
Right.
Yeah.
Thank you.
Yes. And here is like the GIF that is basically showing the example before I was showing, just a little bit better trained. So you see that the red solution is chasing the green solution. And this is trained with just stochastic augmented Lagrangian, which doesn't guarantee constraint satisfaction. So a lot of research is being done in this particular area, parametric programming or learning to optimize, in so-called feasibility restoration layers. Because it can happen that if you don't train it very well, or if your problem is too complicated, your neural network can give you infeasible solution. And there are different approaches for that. And here are this example where we use so-called differentiable optimization layers, that CVXPy layers, to implement basically proximal operator. Yeah, this is a projection on this polytopic constraint. And this is a differentiable layer. So this is a little bit more advanced example. I'm not going to go into details, but there are papers and implementations that allow you to use convex optimization as a layer, as this domain prior, which is very convenient as anytime you want to satisfy some constraints in a hard way with some guarantees. This is very similar or very related to safety filters in control, which, yeah, I see like very much intersectionality in this research that could promote a lot of new research. Yeah, please feel free to ask me more questions as I'm going through more examples. I have like maybe 10, 12 more minutes. I'm going to show this example on neural ordinary differential equations. I'm going to run it again. I guess most of you already know about neural ODs. It's a very neat idea. In this case, I'm using it for identification, system identification of this dynamical system, van der Pol oscillator. But these days, you can see neural ODs used in normalizing flows and especially like in stochastic neural differential equations in score-based generative modeling. So they are all over the place in computer science these days, but the numerical principles behind them are coming from engineering. So there are nice combination of this machine learning with scientific computing. So here we are going to train the system ID model in a standard way, having trajectories of the dynamic system with n step long. Oh, I need to restart this. And so below. Okay, give me a second, importing all of these dependencies. Yeah, okay, while it's importing, I can explain this data set again. It's basically trajectories of step length. Yes, I just computed. That basically cut this whole trajectory of the observed data into smaller chunks. So that's my batch data set. This is the system that I want to approximate and how I'm going to approximate. So there are different ways. You can use like state space models or Koopman approaches. Here I'm going to have this continuous time differential equation model, where the right-hand side, though, is unknown. So it's parameterized by deep neural network. And there are these trainable parameters that I want to optimize. I'm going to use, again, the same multi-layer perceptron that I use for pins and learning to optimize to represent the right-hand side of this differential equation. But because this is a continuous time model, I need to solve this to obtain discrete time solution. So that's the whole idea of this neural ODE, that you have this ODE solver as a layer again. And it can be all sorts of Runge-Kutta family methods, Euler integration, or trapezoidal solvers that you can implement. And now you require gradients to backpropagate the sensitivities of your system ID loss function through this ODE solver, not only through the layers of neural network. And there are two ways how to do that. You either unroll the operations of the ODE solver and use backpropagation through time algorithm, which is basically used for training recurrent neural networks, or use adjoint state method, which avoids unrolling all the operations and introduces the second backward in time equation to provide you with the sensitivities. The advantage of this adjoint state method is that it suffers less from this vanishing and exploding gradient that you have in this backpropagation through time and doesn't require as much memory. But that doesn't mean that this backpropagation time doesn't work always. Yeah, it can work pretty robustly in many applications. Oops. Especially when you have shorter horizon rollouts. So this adjoint state method using this neural network right-hand side, basically that was the whole idea of this neural ODE paper. And the adjoint state method is not new. It has been here for decades again in numerical solvers for differential equations, but it has been brought into the machine learning world by having it as a differential layer. So that's what we provide in the library. We have a list of integrators, either backpropagation over time or these adjoint integrators that have their own classes, and then you just provide the right-hand side you want to integrate. In this case, it will be this multi-layer perceptron. Provide the time step and select method, and you have now basically discretized continuous time ODE as a layer. So you can wrap it in the node class the same way like we did multi-layer perceptron in previous examples. And that represents my model. And this model, I can now do rollout forward in time. And for that purpose, we have this system class, which you can think of it as a symbolic recurrent neural net constructor, which I can define number of steps forward in time. And that would be my dynamic model that I'm actually training with system ID loss functions. And individual loss functions here are residuals between the observed and predicted trajectories. And because this is a smooth trajectories that I have in data set, I can also introduce this finite difference loss. There are many loss functions in system ID or regularizations that help to train these models. This is just one particular example. So then you are solving this system identification problem where you are training the parameters of the neural network that represent the right-hand side of the differential equation to minimize these sampled expectations of the residuals over finite horizon rollouts between the observed trajectories and these finite differences. This you obtain the scalar valued expectation that you can compute sensitivities backward in time through the ODE solver to obtain the parameters of this neural network. And again, I'm using exactly the same API. I'm using the list of objectives and constraints, the same loss functions, and the same problem to construct this optimization problem. And I can also visualize this like high-level computational graph. I have this data set, this machine learning component with the domain prior, which is the ODE solver, and list of objectives that I'm aggregating in this penalty loss function in this case. And I'm using again stochastic gradient descent, the same trainer, the same train method. And after training, I see this fitting. Yeah, oops. And this is open loop prediction. Yeah, how they show like this. Yeah, so I have two states and I'm providing initial conditions and doing forward time in rollout. The magenta is the predicted one and the cyan is the ground truth. So this is very simple dynamical system, so it's easy to fit. But there is a lot of examples in publications. How can you fit these neural ODEs to more complicated, higher dimensional systems? So that's why it's very promising. It's a very universal system identification method for nonlinear dynamical systems. Very often, though, we have some prior knowledge, so you may want to use gray box modeling, and that's what would be like these universal differential equations, or you would like to do Koopman operator or sparse identification of nonlinear dynamics, the SIMD approach. I would argue like this can be unified as all like gray box versions of these neural ODEs if we implement it in the stochastic gradient descent training. So that's what we provide over here. It's like a wide variety of neural operators for differential equations. Any questions on that? If not, let me run this example, which I have only like 5 minutes to finish, which is control. And the idea is the same here. We have differential equation, but instead of fitting the differential equation parameters into the observed trajectories, we want to learn control policy that is parameterized by, let's say, neural network to minimize the expectations of the optimal control objective. So here I'm assuming Y-box approach. So I have this differential equation that represents the dynamics of this coupled two-tank system, which is very canonical textbook problem in control engineering. And I'm going to control the pump modulation and valve opening. And I want to come up with control law, but I don't know the control law, so I will parameterize it with neural network. So here is the ground truth model, and let me run it again from here. Okay, we'll import the dependencies. Here I'm using this differential priority control methodology that we developed in our team, which is again another modality of the scientific machine learning approach, where we are sampling the collocation points of the parametric space of this optimal control problem. The machine learning component is neural network control policy. The domain prior is our system dynamics model, in this case, the ODE, and the loss function is optimal control objective. So how does it look mathematically? You are minimizing the parameters of the control policy here. So this control policy will map the states, and these are the reference trajectories into current control actions. And these current control actions will perturb this differential equation that will be solved with whatever adjoint solver or backpropagation to time algorithm. And these will represent your architectures as layers that you want to optimize with this optimal control objective. So this is reference tracking over finite horizon, some terminal penalty, and we are computing these expectations over m number of samples of parametric scenarios that are sampled from some given distributions. And we want to also satisfy some states and input constraints. There are different ways how to do that. The simplest way is to use penalties, or more advanced ways would actually use like safety filters for projecting onto this solution. That's the method I mentioned with this differentiable optimization layers, for instance. So here I'm sampling the data sets again. I'm skipping that because it's exactly the same like in collocation points and pins. The next step is to define my architecture. So this will be my ODE equation, the white box one. I'm using this Runge-Kutta 4 integrator and using the node class to make it symbolic. So mapping the states and control actions into next states. instantiating the architecture for neural network control policy. That will be another node, mapping states and references into control actions, and making this a system, the closed loop system with control policy and problem parameters. I can show this again. It should visualize, probably still training. I can come back to this in a second. So this closed loop system is the architecture that has dynamics and control policy, and I'm going to train this with this physics-informed loss function that represent optimal control loss, like the reference tracking, penalties on states, and terminal penalty at the final time step. So I can also like select which time trajectories I'm penalizing. So that's also the answer for that obstacle avoidance. When you have like some obstacle, you can also define at which time they enter the frame. So it's quite versatile in that. So here I'm using exactly the same API again, using the same loss function, the same problem class to be trained with stochastic gradient descent using the trainer. So let me stop this training and I should see the solved problem here. So this is the reference tracking on some randomly generated trajectory with my two states that are tracking the time varying reference while staying in the state constraints, and these are the control actions, corresponding control actions. And let me run this cell again, and you should see another randomly generated trajectory that we are tracking. And I can do it again and have another trajectory. And I don't need to recompute the solution over and over like you need to do in real-time optimization. This is parametric solution that has been pre-computed using stochastic gradient descent, and it's encoded in this neural network. So again, you obtain orders of magnitude acceleration compared to interior point solver in real time. So I'm just right on time and I'm stopping here. So thank you very much for your attention. And if you're interested in the library, yeah, please send us feedback either via issues or via discussions.
Thanks, Ján. Is there any questions from the audience?
Dr. Ján, a quick question from my side. I'm Siddharth. So if you're thinking about online learning in terms of in a controlled scenario, if you're thinking about like an online learning wherein you're learning in real time, for instance, an autonomous vehicle or maybe a RC car, for instance, is learning in the real time. Do you think it makes sense to have something like an optimal way of sampling the collocation points instead of sampling it in a greedy way, because that can affect the time taken by the process? So does it make sense to do that, or have you thought about this aspect of it, or does it make sense? Yeah.
This is an excellent question, and absolutely it makes a huge difference. If you're just doing just uniform sampling, you may miss some important points. Like especially if you have systems with active constraints or some sharp boundaries in the solution space, you want to sample close to the proximity of those active constraints. And then when you have part of the solution that is mostly linear or mostly convex, you don't need as many samples. So the active sampling is a very important part of these collocation-based methods.
Yes, because I do realize that if you're thinking about a heat equation for a pin problem, you don't really need to think about an optimal way of sampling it.
Yes.
But the moment you think about a control problem, the time is always, I think the timer is a crucial aspect. So
absolutely, yeah.
And yet another question is like the back propagation in time, which you mentioned for a dynamical system. Do you think the vanishing gradient problem happens when the dynamic system has taken longer time progression, basically? So what I mean to say is like if you're at time step 10, you may not face the vanishing gradient, but as you move to time step 100, you might see that the vanishing gradient is more
absolutely, yeah, because you can think of it like it is a recurrent model. And when the dynamical system especially has a stiff dynamics, so when there is like a large conditioning number, higher eigenvalues, smaller eigenvalues.
Right.
The smaller eigenvalues will vanish very quickly. Higher eigenvalues, if they are unstable, they will explode. So a lot of like the conditioning methods, numerical methods can be used here to treat that.
So does it make sense to have shorter time steps as you make good progression in time to have
Yeah.
a shorter time steps and still you can avoid the vanishing gradient with if you're using the backpropagation?
Yes,
time?
that's the good way to start. Start
Okay,
training with short horizons, and then there is a method what they call curriculum learning.
Right.
Then you can progressively train with longer horizons. So starting with smaller, simpler problem, going to the more complex problems. And that's also related to homotopy methods in constraint optimization.
Oh, okay.
Yeah, so it's very interesting how different ideas have been developed, different
Yeah.
communities, they're called different things.
Yes, definitely. I mean, thank you for all these insights. I mean, it was really a great talk for me
Yeah,
personally.
thank you very much. And happy to be here. Very great questions.
Is there any other question? If not, I have one. Well, you already said that this is really fast. Speed up is really great, the Neuromancer compared to the traditional methods. But we can still is the scalable or parallel version of this Neuromancer available, or it just this is the serial one, right?
Yes, so we have that PyTorch Lightning integration examples that allows you to parallelize the use multiple GPUs to train the models and do hyperparameter tuning with weights and biases. So that's for larger problems. What we have in the baseline examples are very prototypical CPU examples, small academic examples.
Okay.
Yeah. So we build the library on top of PyTorch also because of the ease of use, but also of the scalability. So all the tools they develop for machine learning, we can basically leverage for these type of engineering applications.
Okay.
Yeah.
Thanks, Jan, for the great talk. And if there are no questions, we can stop here.
Thank you very much, everyone.
Thank you.
Have a wonderful day.
Thank you.